Ladies and gentlemen, now we have our next keynote speaker, Mr. Antonin Ancelle. Antonin Ancelle is a manager of embedded targets development for MathWorks, leading an organization responsible for all aspects of software development. Product and technology strategy, software development phases, partner management, strategic planning of innovative solutions, providing model-based design for Raspberry Pi, Arduino, BeagleBone Black, ARM Cortex-M, TIMCUs, and other embedded targets. He created Embedded Targets Development Team in Bangalore, in India, in July 2011, after 3 years in France and 2 years in US, where he joined MathWorks as Embedded Target Developer in 2005. Prior to joining MathWorks, he worked as embedded software engineer developing motor control algorithm for UQM technologies. He has his bachelor's and master's degree in electrical engineering from Paris Sud University, as well as master's in electrical engineering from University of Colorado at Denver. Now I request Mr. N.B. Pasulkar to felicitate him with a memento and bouquet.
Thank you very much. Thank you very much.
On behalf of Instrumentation and Control Department, College of Engineering, Pune, I would like to call upon Mr. Antonin Ancelle to deliver a keynote speech on building the future of intelligent systems with model-based design.
Thank you very much. That's a very heartwarming introduction for me. So I'm Antonin. I apologize right away. I'm a software developer. I have poor presentation skills, so I'll do my best to introduce my topic today. And I think it's a nice segue from Dr. Lee, because I'm going to talk mostly about software. And we heard about hardware. Now we'll hear about how to control this hardware and how to use our computers to control these intelligent systems. So I have a pretty ambitious topic today, building the future of intelligent system with model-based design. So I guess my first question to you is, what is the future going to be like? When I was told I would talk to a college of engineering, for me education sounds like future. You guys are going to build the future of what we're going to see in 20 years. So basically, what is the future going to be like? We know a lot today, but do we really know what's going to be there in 20 years? What are going to be our intelligent system of the future? So to best answer this question, I went back about 20 years back and see what we had, what was the vision of the future back in 1985. So when I was a kid, the future was flying cars. I hope you've all seen Back to the Future, which was a very popular movie at that time. And this is the DeLorean car, which was supposed to fly in October 21st, 2015. So that was the prediction of the future at that time. Unfortunately, this is not really happening. Though, back in 2011, I was at the Aero India, and I saw the Bangalorean, which was the Indian version of the DeLorean. And that was the flying Maruti car. So some people have actually tried to achieve that goal of flying cars. But I guess this is not really the present. Flying cars are kind of behind. That was the vision of the future we had 20 years back. Today that vision has changed. And these are other objects that we had imagined like years back of being the future. And I think the future is a little different. Well, at least the vision we have today is not exactly what it was like 30 years back. So basically, I want to make a statement here. I don't think we have excelled at predicting the futures. As a kid, we were supposed to be seeing flying cars by today. I'm still driving a four-wheel car. I think voice recognition was a big thing in the 90s. My first computer had a microphone. I was supposed to control my computer with no keyboards. I had that new phone about 2 months back. I started texting using that voice recognition. After two days, I stopped doing this. I think this is still, has to improve. And whether this is going to control the future, I'm not that sure. You see all these movies where voice recognition and voice activation is part of the future, but is that really going to be the case? So self-driving car is something that we hear about today a lot. Google is investing a lot of money in these self-driving cars. Do you think we're going to see self-driving cars in 10 years in India? I see that hand's shaking. I was in my taxi cab this morning, and yeah, I was thinking about this, and I saw all this traffic. I'm like, how is a computer going to handle this? Right? But yeah, so I'm questioning, are we really good at predicting the future? I was actually in a conference exactly 10 years back. That was in 2005. I was in the Silicon Valley in Palo Alto, and there was a GSPX conference. I was a fairly young engineer at that time, and Andrew Viterbi was giving a speech. And he was talking, at that time he was talking about 3G and smartphone. He was actually questioning the fact that we would send emails, and he was showing his phone with like 12 keys. It's like, how am I going to send an email with these 12 keys? We're coming up with a 3G network with a lot of bandwidth, but how are we going to use this? And he was questioning the fact that, do we really need that 3G? So for those of you who don't know Andrew Viterbi, he's the inventor of the CDMA algorithm, which is widely used for cell communications, and he's also the co-founder of Qualcomm. So he was actually questioning this. So I think, today we found a very good use case for this 3G network. Actually, today I want 4G. I think that 3G is too slow to me. So basically, though he was not really sure how we would use that 3G network, he was still convinced that we had to do it. And he was investing a lot of money. I think Qualcomm is actually well positioned in that market today. So I guess where I want to get to is we may not be so good at predicting the future, but we may be actually good at predicting what needs to be done to enable the future. So some people have succeeded. I found that picture online. So RCA transistors in 1964. And the pitch is, this is how RCA transistor will run your electronic car of tomorrow. And if you see that car, I kind of like that picture because it has that, it looks like an oscilloscope, in between the two front seats of the car. That's actually a pretty good vision of the future, because now you have that nice screen with all your, mapping system and gadgets for your car. So I think that was a pretty good vision of the future. Now, they bring a good point, this RCA, because they were building transistors. The transistor today is the base of these intelligent systems. Transistors they were invented in 1948, and actually Intel is predicting that 170 billion transistors will be in this world per person by the end of 2015. Just in the main CPU of the iPhone, you have 2 billion transistors. One question I wanted to ask, how many of you have a smartphone in your pocket? All right, I think that's the entire room. And just for my personal interest, how many of you have an Android-based smartphone? All right, that's like what, 75%. Apple-based? Okay, 5, 6, okay. What about Windows? Hey, about the same. Okay, thanks for the feedback, because I need to build some mobile applications. I need to know what I need to know where to focus. I think Android is good for India. All right, so the transistor is the base. So basically, investing in the base is definitely a good choice. If you find that base, then people will build on top of it and invent intelligent systems. So that's why RCA was so good at predicting the future because they were building in the base and they were right about finding that base. So what do we do today? What is going to be the future of tomorrow? I'm still trying to answer that question. So if we look at the most innovative companies and some of the smartest projects, we can see that Google, so Google is famous for the search engine, they're now investing in solar drones. And they want to provide internet to remote places. Obviously, if people have internet in remote places, they'll be able to use their search engine and their social media products, and that's more business for them. And guess what? Facebook is doing the same. So there are a lot of new flying objects that are supposed to happen. We didn't see the flying cars, but maybe we'll see these, or at least that's what they predict. We also have Amazon coming up with flying drones to deliver your Flipkart item, or I guess this is Amazon, but they want also to have flying objects to deliver things to you. These companies are kind of far away from their core business. They are doing search engines, social media, and now they're inventing intelligent systems to try to enhance this. So their vision is to intelligent system to grow up the business. That's the vision of the future. So there's one example I want to dig into, and I talked briefly about it, that self-driving car or driverless car, so the Google car. They claim that they have covered thousands of kilometers on real traffic today. I also read that they had 11 accidents, but it seems like the system is not at fault. But yeah, this is something that a lot of people talk about as the future. So do we really think that's going to be on the roads tomorrow? There's still a question, and in my mind, I have some serious doubts that this will be actively the future. Now, even though I have doubts that this may be the future, same as Viterbi back 10 years back, one thing I'm convinced about is definitely we're going to see much more intelligent system in the car. And that has a name now. It's called ADAS, or Advanced Driving Assistance System. So your car is going to become much more intelligent. And because of these people trying to create self-driven car, they're going to do research into how to detect the car in front of you, how to detect if there's a pedestrian, if there's someone behind. So all these systems are real, and they will be in the future tomorrow. So adaptive cruise control, intelligent headlamp control, blind spot detection, lane change assist, backup assist. How nice would it be if your car could just park itself? That's feasible. I can see that happening. Lane departure warning, you're falling asleep and the car tells you, hey, wake up. That's definitely feasible. I can see that going in the future. So definitely the direction we're taking is going to set some base that we will use in the future. So that's what I'm trying to get. Even though these ideas may sound like too futuristic, they will pave the way, and they will create systems that will survive for sure. So one thing I took from the web, from a silicon vendor, this is their ADAS chip. Okay, so this is what they put on the market to help create these lane departure detection. So I took it from TI. Every vendor, every silicon vendor is coming up with their own. One thing I want to point out is, so look at this chip. It has two Cortex-A15 processors. It has two dual-core Cortex-M4 processors. It has two 66X floating point DSPs. I talked this morning with Roshan Patel. If you don't know what these are, you can take his class on the 6713 processor. So this is a DSP, digital signal processor. And it has vision acceleration, 10 UARTs, 2 CAN buses, 4 SPIs, etc., etc. How do you program this? I mean, seriously, when I looked at this, I I learned C and I did a bit of assembly, it would take me my entire career to come up with something that works on this platform. It's very complex. It has so many processors. So where I want to get to is C is not powerful enough, or it is, but you need some high-level programming language to be able to program such a complex device. And we at MathWorks are coming up with model-based design. And that's what we believe is the base for the future of programming these intelligent systems. You'll need thousands of lines of C code to program the device I showed earlier. So you need a strategy. You can't just go ahead and say, okay, I'm going to try to program that device, and you start writing C code. It's not going to happen. So, so basically, let me introduce model-based design and try to explore how this can be the base of programming the future of intelligent systems. So we start with models. What are models? Simulink is a graphical programming language. It's a simulation tool. So you start with your model, and your model becomes your specification of your system. You kind of draw your model the same way you would explain your system is working on a whiteboard. You know, you get your sensors from the left side, you have your algorithm in the middle, maybe with a feedback loop, and you would actuate some actuators. So you have your specification, so the model acts as a way to describe what the system does. You can use it to simulate. You press the play button, and that runs a simulation. You can watch what your system is doing. And now the most powerful tool in my mind is you can press a button, and that generates thousands of lines of C code, and that goes into your system and programs your system. So you can concentrate, like Dr. Lee said earlier on, you can concentrate on what's of interest to you and start abstracting what's maybe less of interest, and you can start focusing on the intelligence of the system rather than how to get the data from that sensor and format it in a way that it's manageable. So obviously that's more for the industry, but yeah, you need to test this. So how do you make sure your system works? By the way, when you go on a piece of hardware, it never works the first time, right? You always have to debug, understand why it doesn't work. So you need a way to watch these signals and interact with the system in real time, so you can debug and understand how to correct your problem. So that's our foundation. That's our vision of how we can make an impact on the future. I'm not sure exactly what the future is going to be, but I'm sure we're going to need these high-level programming techniques so we can build whatever is going to be in 20 years that you will create. So I'm going to go through more detailed example. Like I said, I'm a developer, so I'm going to be in my comfort zone now. So this is a digital power supply, and we've done that workflow around that digital power supply platform. That could be also a Quasar equipment. This is just an example of something simple that we can work on. So we want to try to program that digital power supply. It's a hot topic in the industry these days. We can save a lot of energy if we have better power supplies. Nowadays, your cell phone charger is wasting about 50% of the electric energy it gets from the plug. That gets dissipated in heat, and we can do much better in power supplies. That's why it's so important these days. We're trying to save that energy. So basically, you start with a physical system that you want to control, and in that case, it's that power supply. What's the problem that we're trying to solve with power supplies? So voltage is a physical quantity that changes very fast. So you need to react, within 2 to 10 microseconds. That's about 100 to 500 kilohertz. That's what's needed to react on a fast changing voltage. We need advanced control algorithms. That's how we're going to create that efficient way to not lose energy. And basically, that's what we need to implement. So first of all, we need to design with simulation. So So we need to create a physical model of our system. And for that, we introduced the Simscape language. I'll talk briefly about what that is. And then we need to simulate this with a solver. And that's what Simulink provides. Provides a way to solve differential equation from the system and show the behavior of that system. And then you can go into some average modeling. You can go in very fine details and start seeing how your PWM is transitioning. So that's a model of the physical system. You can recognize, it's kind of small here, but you can recognize inductances and resistors, and that's basically what I have in my power supply. You can see these colors. The blue color is electric wires, and that brown color is my measurements and my control signals. The black signals are my controllers. So basically, you can see that the black signals have a little arrow. That means it's data flow. So in Simulink, there's a concept of data flow, data going from one block to another. You can see that the electrical system doesn't have any arrow, because an electric system, one component affects the other, and the other affects the first one. It's a bidirectional connection. So that's represented in that diagram with arrows, colors, and that's how you create your system. Now, one thing I want to point to, without going into too many details, I know it's still the morning and it's Friday, but look at this inductance. So here we have that component, and this is how you describe it in the system language. So what I want to focus on is that equation. The way you describe that component, you just have to put the equation, and you can notice the .der, .der. What do you think that .der means? So I have V equals, and let's just look at the last term. It says L times I dot der. So we all know that the equation for an inductance is I times, di over dt, right? So the dot der is the derivative of the current. And that's what you've learned, you've learned that a long time back, I hope. But that's how you describe the behavior of an inductance. So basically we created a language which is based on the MATLAB language, high level, easy to understand, you don't have to specify your data types and things like that. And that's the Simscape way of describing a physical component. And we tried it to make it exactly the way it is in your textbook. You need rigor, like Dr. Lee said. You need to understand what this does. Do we really need to understand how this is computed in the background? I'm not sure we really do, as long as we understand how the component behaves. So that's how you describe your component in the Simscape language. So just by seeing this, let's imagine you have a very complex control system. You can come up with equations that describe that system, differential equations. And just by looking at the way you specify this equation, I hope you can project how you can create such a component in that Simscape language to be able to simulate it. So we at MathWorks have tried to abstract this as much as possible to make it the most simple. I mean, I don't want to say easy, because at the end of the day, it's still complicated what you try to do. But at least we can focus on what's of interest to us and abstract how to manipulate that data. So that's the Simscape language, and then that's what we use for simulation. Now you can test your controller against that physical system. And here, this is actually a DC to DC buck converter demo, and we're adding a load in the system every 2 seconds. So that's why this graph is kind of shaped like that. So every 2 seconds, we're adding a load in the system, and we check how the voltage reacts when you start adding a load. So we're at the second level, and we're simulating how we add that load and how the system behaves. And you can play with your control algorithm, see if the overshoot is acceptable, if it's too much, and you can start tuning your controller this way. At the same time, depending on how you set your solver, you can go at the PWM level. So here I zoomed on that spike that you were seeing on the previous slide, and you can see that it's not as smooth as we would see. Now I'm at the microsecond level, And here the little spikes you see is the PWM. PWM is the digital way of creating analog signals. They introduced these little spikes, so you may also get to that fine level of granularity and see if that's acceptable to you. Now, once you're happy with this, we have a tool, very powerful tool, that allows you to generate C code for that controller. And that C code you can directly embed onto your system and start playing with it. That generates thousands of lines of C code. This is a huge added benefit for our customers and also for you. You don't have to come up with these thousands of lines. You really concentrate on your algorithm. I talked briefly about our techniques to integrate optimized functions. We have a way. Our code generator is becoming very smart. It has started maybe 15 years back, and now we're going into a very detailed way of making it optimized. For example, your processor may have some optimized functions that is provided by the silicon vendor. We have ways to replace nodes, and nodes are calculation, multiplies, divide, additions, with optimized functions if you provide them in a table that we open to you. So that's what we call CRL. We have a lot of techniques like that to make that code generator very efficient. We have processor in the loop, so that allows you to verify that the algorithm that you've created is matching what you have simulated. So the way it works is you take that subsystem in your model, you load it on your hardware, and you're able, with a communication channel, to send data to the system, get data back from the system, and start visualizing if that's matching what you have simulated. Of course, if the code we generate is different from what you have simulated, then it's not going to work. So that's a necessary technique to verify that what you have done is correct. As part of this, you can start measuring how much time it takes to run on the hardware, see if your control loop is fast enough, and you will be able to match that 500 kilohertz requirement that you may have to do your power supply. And that's the pill profiling that we offer. Then what we try to do, and that's the reason why I go so much into details, is because a lot of this is developed now in Bangalore, and we try to provide a lot of hardware concepts back at the Simulink level, back at the modeling level. So when you go on an embedded system, you need to react on interrupts. You need to read from an analog to digital converter. You need to send data to PWM, to serial. You need to interact with a lot of physical blocks. And what we try to do is we try to bring these concepts back into the Simulink model. So here I'm showing the model of that buck converter. And you can see, I'm not sure you can see, but basically we have this block here, which is a hardware interrupt. So the hardware interrupt triggers the subsystem. And basically this is triggering when my ADC conversion has complete. So I can go into very detailed embedded specification of the system back at the Simulink level and try to work with these hardware concepts back at the modeling level. By the way, this block is being developed in Bangalore now. So the design is happening in Bangalore. We're not trying to outsource in India. We have a R&D center, which is fairly small. We hire bright students like you are to do these complex design. Actually, at the end of the day, we think it's pretty simple. We try to abstract like the dot dir that I showed before. This is our way to react on an interrupt. We just have a block and we trigger a subsystem, and that's a nice graphical vision of the reaction on an interrupt to trigger a piece of code. So we have some peak current mode controller. We're going deep into how to control this power supply and how to implement these new smart algorithms that will allow you to save power and be more efficient. So we have a lot of blocks that support, in this case, it's a TI-C2000. This is just an example. we have block sets for many other processors. And that's what we're trying to develop. We're trying to make the connection between software and hardware the smoothest as possible. Another very important point of model-based design is the ability to watch in real time what your system is doing. So once you've loaded this code on the hardware, we have tools to visualize what's happening, bring back the signals back into Simulink, look at them on oscilloscopes, and we can tune parameters in real time. You can change your PID gains, see what the system how the system is reacting. So everything I showed actually was applied by Fujitsu, and that's the reason why I'm showing it today. They created their server power supply, so they designed a server power supply that they sell today. That's the workflow, the exact workflow they used. So that's actually in production today by Fujitsu. So I guess that my goal was to try to show you the workflow, what we do with model-based design, and how we change the way of programming compared to traditional handwritten C code, and the approach we use to make sure the system is safe, and what you have designed is actually what's running on the hardware. So I'm going to give you a few examples of model-based design being used in the industry. So here I have Delphi. I'm going back to my self-driven car. So Delphi is creating scanning radars, and they use model-based design to do so. They presented their work, and basically what they have said is basically the code is reliable, efficient, and you know, they haven't found a bug yet, and they have run it for 1 year. So this is pretty remarkable. They've created a system where for 1 year it's been working with no bugs. I think this is really hard to do if you just use traditional techniques. Another example is from Continental. Dr. Alexander Burns, he presented in our MATLAB Expo in Germany, and he's doing some video recognition system, trying to recognize traffic signs and applying this to the auto industry. So this is real. This is happening now. People are creating these intelligent systems using model-based design. In this case, Conti, they used image processing toolbox, signal processing toolbox, statistics and machine learning toolboxes. So I have some other examples. This is a video of the Orion spacecraft. So this is the new way that NASA wants to get humans to space. So that's the launch of the Orion spacecraft on a Delta IV heavy weight rocket, and they also used model-based design. So basically, this is the rocket, and I think it's going to go back to the atmosphere. They kind of changed the technique compared to the Discovery shuttle, but now they use more traditional technique. But basically, what they claim is they navigated from launch to landing using GPS and inertial sensors, and all of that was on auto-generated code. Every single line of code of that system is generated by Simulink. So basically, what I want to get to is we need to find new ways of programming these systems. Okay, so how will students prepare for model-based design? What can you do if you want to learn these techniques? So you can come up with a lot of ideas, and there are already a lot of platforms that allow you to exercise your skills. So there are some Rubik's Cube solvers, some weather station. There are a lot of robotic competitions that are out there that you can play with and use model-based design. We have software to hardware connectivities for a lot of intelligent systems. I put just a few examples. This is the RoboCup that's happening in Europe. They're trying to have robots play soccer. They've been conducting this robotic competitions for many years now, and they're adding categories. That's the mid-size category. So you can see the field is about like, I don't know, like 20 meters long. They have a smaller category where the field is more like a TT table kind of size, and now they have the humanoid category. So you have some robots with 2 legs, like the one we saw, and in Dr. Lee's presentation, and they're trying to see how robots can be better than humans at playing soccer, and their goal is to do that by 2015. So that's one area where a lot of teams now are fully using model-based design to control these systems. And this is pretty complex. Can you imagine trying to come up with an algorithm that plays soccer, pass the ball, receives the ball from another player? This is non-trivial to do. And at the end of the day, it's pretty amazing what these robots are able to do. I have another video from University of Pennsylvania, where they try to fly quadcopters in a formation and try to have them do something in sand. So this is also something where they purely use model-based design to solve these problems. And that's a pretty impressive application that they're managing to do. All right, I like that video. That was 2 months back. So that was back in Bangalore. I remember actually meeting with a few students from Pune. I'm not sure it was from COEP, but definitely there were students from Pune. That was the Freescale Cup. So Freescale is hosting that cup. I guess they're going to be called NXT soon. But they're hosting that cup every year, and the goal is to program a little car. They give you the hardware if you participate in the cup, and you also get MathWorks software. So you can really concentrate purely on your idea to make that car the fastest. And this is what makes the difference in this competition. So that happened in Bangalore at IESC 2 months back. That was the beginning of April. And I was really amazed to see all these students participating in this competition. Like Dr. Lee was saying, you could feel that energy and motivation to build these systems. So we see a lot of energy, and I guess what we're trying to do is find the ways for you to express these ideas that you may have. All right, so I'm going to talk a bit about low-cost hardware. This is Dr. Lee talked about trends. We're thinking that this is definitely a trend. What used to cost like $500 US yesterday costs now $30. And if you don't have it in your university, you can buy it for a home. Who has bought? I want to check this. Who has bought a cheap piece of hardware for home use, like a Raspberry Pi or an Arduino or a Launchpad? Who has bought this? All right. I have bought for myself. But yeah, I can see there's about 20 people in this room. This is definitely something that's changing. That was not possible a few years back. It was possible, but you needed to be like a rich person and dedicate your money into this. Now you don't even know what you're going to do with it, but you think it's cool and you're just buying it because you want to play around and start, putting your ideas into this system. So this is definitely something changing, and we're trying to address this. So we're creating these support packages for all these new hardware, so you can abstract yourself from that complexity of getting data and accessing that peripheral. We're trying to provide blocks for you to do this, and you can really concentrate on, hey, let me do fire detector, so I can put it in my home, and if the heat is too much, it will ring my cell phone, or things like that. So there are a lot of low-cost hardware platforms, and we have multiple ways to access this. We have a tethered way. So the tethered way is you're in the MATLAB environment, and you can write MATLAB commands, and your hardware is connected to your computer, and you can directly interact with the hardware. So you can say, okay, get me that ADC, and it will return the value of that analog to digital sensor. That is the tethered way. You can write a script, MATLAB script, high-level language, easy to program, and you will get data from your hardware, and you will be able send data to the hardware and do something. We also have the embedded way of doing things. That's what I showed with the Fujitsu use case, where you create a Simulink model, you generate code out of it, and you load it on the system, and it becomes like a fully autonomous system. And it's not connected to your computer anymore. Or it may be if you want to gather data, but the goal is to have a fully autonomous system. So I guess these are the two ways that we're approaching this accessing hardware. If you're interested, just go on mathworks.in/hardware, and you have a list of all the hardware that we support. We keep adding new things. We try to support the newest and coolest hardware that's there. We have a lot of partners. Quanzer is one of them, and people are also enabled to create their own hardware support. So yeah, as an example, we support the Lego Mindstone EV3, and we have support for the new Android phones. That's why that was important for me to know how many people use Android. All right, here's another video of, I kind of like that video. This is a person who's he's the bilateral amputee, and basically this is an example of how we used model-based design. You can see on that video, there's an arm on this screen. You can see that arm which is moving. So it starts with simulation. We have connected sensors on the termination of his nerves. So that's how we get the signals from what he wants to do. He thinks that he wants to move his arm, and that creates an electric signal on his nerves, and we're sensing this. And we first work in simulation purely, this is connected to his computer, and we're trying to move the arm virtually. And at the end of the day, we're connecting arms to his body, and we're doing the same in reality. And you can see this is pretty amazing. You can grab a ball and putting it on a shelf. You can imagine how this can change people's life. Programming this in C is very difficult. If we have smart way of programming these intelligent systems, we can change the world. This is really an application that's going to change his life. And think about the possibilities you can do with these smart programming techniques. So I guess, yeah, there are a lot of new areas. I'm going back to predicting what the future will be. So SpaceX, I think this is a very interesting example. This private company launching spacecraft, and they're trying to make it really cheap. If it's cheap, that means it's going to be accessible to a lot of people. That means tomorrow you're going to be able to create a small satellite. Actually, I thought that was very interesting because India was they created that mission to go to Mars, and I think Modi claimed that they went there cheaper than an auto ride in Ahmedabad, which I thought was pretty interesting. And if you think about it, so there is the CubeSat. CubeSat is a very cool application. It's a 1 kilogram, 10 centimeter cube that you can put in that SpaceX spacecraft, and you can book a space for $50,000. If you think about it, $50,000 is not that much to launch something in space. How much is that? Like 30 lakhs, right? And you could probably buy an apartment for that price. So for the same price, you can launch a cube in the space, which is accessible. You can imagine this. That's not that was not possible like 10 years back. Nobody could think about, hey, I'm going to launch a cube into space. Well, so that you can book that cube and you can start imagining something cool you can do from a satellite. So I think these are interesting things of things that we will see in the future. I'm also pointing to some R&D that's happening in India. There are about 200,000 jobs that are going to be created in R&D in India by 2015, and this is out of the Zinov report. So this is growing like exponentially. Yeah, so a lot of engineering and R&D happening in India. So I guess my conclusion is, I'm not sure what intelligent systems will do in the future. And I don't think many people have a good answers for this. But what I'm convinced about is we need to equip people with the right tools so they can implement their ideas. And definitely the same way RCA was planning this transistor, I'm foreseeing model-based design to be the route for creating the future of programming intelligent system. So I would encourage you to learn this and be engineers that are going to create these systems of the future. So that's all I have. I thought that was interesting for you. I have a small note at the bottom of this screen. I'm looking for smart students for internships, and we're going to build these smart system out of Bangalore. So I put my email address. Please don't spam me too much. But thank you very much. And I'll take any questions if you have any. Don't be shy. Even if you think you have a dumb question.
We observe two types of products in the market. One is that the companies who are into the hardware and they claim that we use the Simulink platform, say to quote DSpace and OpenRT sort of environment. And then here you claim that we also have a hardware. So as a user, we get confused sometimes. So performance wise, or what should as a user look at while selecting either a OpenRT or DSpace sort of hardware, or what you have shown these to facilitate HIL and real-time simulations.
Okay. Okay. So the question is about which hardware to pick and how to make that decision. And you mentioned DSpace and OpenRT. Without going into too many details, I think every piece of hardware has a focus in one market segment. I think OpenRT is very good for HIL, and OpenRT excel in doing a physical simulation of a system back in a system that will do it in real time. When you simulate your system in Simulink, it's non-real time. 1 second of real life may take 1 hour if it's really complex, may take 10 milliseconds if it's really easy for Simulink to compute. But in any case, Simulink will try to do it as fast as possible. And that's the way you do on your host. Now, OpenRT will provide you with a way to run that simulation, simulation of the physical system in a box that will be able to achieve real time. And they have this FPGA solution. They try to make that really fast. I think that's their focus. On the other hand, when you go to DSpace, for example, they try to focus more on the control. Their goal is not to simulate a physical system. They'll try to focus on the control. We have XPC Target, which is now called Simulink Real Time, which is focusing on both control and physical systems. And depending on the option you find, you try to pick in your box, you can make it targeted more for simulating a physical system or simulating a control system. Now, one thing I want to say is sometimes people go for a very powerful system. These powerful systems are sometimes hard to control because they run an OS, right? There is embedded Linux running, and though you will be able to run a lot of computation, the turnaround time, how often you will be able to go back to your loop, your 500 kilohertz in that control algorithm, will be very difficult because you have that OS in the loop. What we're trying to do with the small boards, the TI boards, for example, the ST boards, we're coming up with a bare-board scheduler, bare-bone scheduler. So that you don't have any OS, you have control of all the low-level hardware. That allows you to react really fast. And for control algorithms, I would actually recommend to go with a bare-bone platform, something you're fully in control. For something more complicated, you can go for a high-level equipment, like Simulink Real-Time. And if you try to do HIL, then you can look at other systems. So I think it really depends what you're trying to do. The type of simulation, is it controls? I think the application makes a difference. If you're trying to do video, then obviously you're not going to pick the same hardware as if you're trying to do tight controls. So yeah, my answer to this would be
Case to case.
yeah, case by case, and really focus on what you're trying to do. And you know, we're here to help. We can answer these questions for you depending on your particular application.
Thank you. Thank you.
Very good question. Thank you. Yeah.
So I've been using model-based design for a semi-active suspension system.
Yeah.
So I want to control by just like a virtual instrumentation. So I use a CDA. So I have designed the model equation in Simulink.
Yeah.
So I want to control the real system. But the problem is that the Simulink has withdrawn its support for CDA after 2008.
For CDA.
Compact DAQ.
Okay.
That CDAQ means binational.
Okay. Yeah, maybe it's because of National Instruments. I don't know. I don't have the reason why we dropped this support. To be honest with you, I was not aware of this piece of hardware. One thing I can say is you probably noticed for the MATLAB users, we try to open as many things as possible. Our goal is not to close doors. We try to make it as simple as possible for you to extend the tools. Most of the hardware extension that we provide is now based on documented APIs. So if you have your own system, or if you know you want to control your system in a particular way, you can actually build that hardware extension. We also have our social media, social file exchange website. It's called MATLAB Central. On MATLAB Central today, you find a lot of people extending hardware and publishing their solutions. So what I would recommend, I mean, I'm not sure I'm answering directly your particular question, but what I would recommend is if something you're trying to, a piece of hardware you're trying to access is not available, I would try to see if some other people have provided support that they have published on the file exchange, or if you can do this, if you can read our documented APIs, try to come up with that support, and just publish it so other people like you can reuse it. I think that would be my best answer. Any other questions? Yep.
So actually, in this year's Robocon,
Yep.
it was required to track a moving shuttle.
Okay.
Right. So what we did was that we were initially using Simulink modeling to have these image processing algorithms implemented. But what we found was that MathWorks and MATLAB tended to be a bit slow.
Okay.
So we had to convert it into OpenCV. So what are your views about this?
Okay. You converted to OpenCV.
Yes. So we had to convert the code. We had
Okay.
to finally build a system in OpenCV.
Okay. So let me ask you this question. So did you try to generate C code out of this model?
Yes.
Okay.
It's actually just testing it, whether it would work or not, and finally we had to convert it.
Okay. So we have a tool called Embedded Coder, and that tool is basically one layer on top of the code generator. That tool provides a lot of ways for you to tune the code. Sometimes you have to help a bit the engine. You have to tell the engine, okay, I'm running on a Cortex M4 processor, and ARM provides me with this CMSys library that has a bunch of optimized functions. You can tell the code generator that each time you find a multiply function with some fixed point data types, well, you can replace that function with a function from the CMSys library. So this is one way you can optimize your code. I think there are also a list of best practices so you don't fall into traps of carrying vectors from one block to another and increasing that memory copy. I'm just giving you these two examples of ways to optimize the C code, but basically we have a lot of techniques to optimize the generated code. Once you're familiar with these code generation techniques, it's almost impossible to beat the system with handwritten C code. Basically, what I would advise is instead of trying to rewrite the C code, work at the Simulink level, play with these levers to try to change the engine to be smarter with respect to what you want to do. So that would be my answer to this. There are a lot of ways, and you can use the local help here that we have now a MathWorks office in Pune with bright people who are here to help you. I would follow these avenues, try to see if you can reach your requirements.
Just to add, we are supporting Robocon.
Oh, okay.
So all the 89 participating teams have access to the MATLAB, all the toolboxes.
Oh, great.
Here.
Okay.
So that includes the encoder, whatever they require.
Oh, great.
So
Okay.
they have resources available and technical guys on whom you can.
Yeah, and why don't you stop by? We have a booth today, actually. You can stop by and we can start going into the details of your question. Thanks a lot. Any other questions?
Just to make a comment.
Yes.
From the educator's perspective, I've been teaching control systems since last 8 years. And model-based design is really nice to do sophisticated projects for our students. But as an educator, I would like my students to spend more time on the fundamentals, and I would like to expose them to this kind of tool only the later stage. That is, I will take the prerogative to decide when to expose them to this kind of tool, because students are not spending much time with the fundamentals, modeling and
Okay. I guess our goal is to try to abstract we're not trying to extract the fundamentals. Definitely, and I think that goes back to what Dr. Lee was saying. Rigor has to be there. You need to understand what you're doing. If you lose the understanding, if you start doing things you don't fully understand, I don't think you're going to go really far. So we're not trying to abstract you from the fundamentals. What we're trying to do is to make it easier for you to concentrate on what's important. And we definitely try to abstract, getting data. We're trying to be the calculator of what was like 20 years back. You learn how to do some math. At some point, once you know how to do it, if you have to do a complex calculation, well, there's no point of writing it on a piece of paper and solving it every time. You just put it in your computer, you run it, and it gives you the result. So that's what we're trying to do with fetching data from a sensor. You do it once to learn how this is being done. Once you've done it once, it's pointless to repeat it and repeat it again. Just use a block that gets the data, and that's pretty complex actually. Sometimes you have to use concepts like DMA or interrupts and very low level hardware concepts, and we're trying to abstract that and so you can get the data, and then you can focus on the fundamentals of what to do with that data. And that could be a filter, that could be your Kalman filters or PID controllers, and what we hope is actually these tools help you to focus on the fundamentals. Any other questions? All right, it was a big pleasure for me to be here, and thanks a lot for that.
Thank you, sir. So now I request T.S. Chandar sir to please conclude the program.
Thanks. It was a nice lecture. I think there was a lot of audience who had a lot of queries on this. Thanks once again, and one more round of applause.
Thank you.
Few announcements are there. Today we have arranged a banquet dinner at Pan Card Club, Bane. So all the participants are requested that after your presentation get completed, please be there at sharp 7:30 at our main building. Bus is made available for you. So please be there at 7:30 sharp for your transportation. And for all our foreign nationals, different separate transportation is made available. So for that, please contact PD Shenge sir or our registration desk. And one more announcement for today's participants. Please make sure that your presentation is being loaded at your particular classrooms prior to your sessions. And for a first year MTech and second year MTech of COEP, those who are interested for the internship at MathWorks, as Antonin sir has said, so there is a meeting at 2:30 p.m. sharp. So please be there in Mini Audi at 2:30 p.m. Thank you. Thank you, one and all.